All right, Algebra 2, we are going to start Unit 7, Lesson 10 today. So we're going to start estimating proportions from samples. So let's see if I can get this to work. Come on, work for me. It's not working. There we go. Sorry. Okay, so we're going to estimate the population of proportions with some data. So for right now, this is the warm-up we did in class. What I would like you to do is mentally evaluate the proportion of chips that are blue. So for the first one, 17 are blue out of the 50 chips. Then for the next one, 28 are blue out of the 50 chips. Then 17 are blue out of the 20 chips. And then 21 are blue out of the 60 chips. So go ahead and hit pause and write those down in your notes. If you're following along in your book, we are on page, I got it right here for you guys. We are on page 234, and those questions are at the top of that page. So write those in. Okay, so when I was working through this, the way I came up with this is I got 17 out of 50, and that would equal 0.34. Another strategy that we could do is doubling it. Since we know that any number over 100 is going to be our percent, we could have doubled the 17 because double of 50 is 100. So then we would get 34 out of 100, which is still 0.34. So if we use that same strategy of doubling, we get double of 28, which is 56 out of 100. And that's going to equal 56 or 0.56, excuse me, so 56%. This one's a little bit harder, but we still can do it. I think I'm going to just do the shorthand of 17 out of 20 and then type that in my calculator, and I get 0.85. Again, we could have divided each by 2 and gotten the same. So 17 out of 20 is the same as 8.5 out of 10. So, I mean, whatever works for you, however you want to do it mentally, because we can't use a calculator to get that. So if we said that half of 20 is 10 and half of 17 is 8.5, that makes it so we can see that this would be 85%, right? And then the same is true here. So this one is, again, a little bit tricky. So 21 out of 60 would be the same. If we were simplifying that down, we could do that 7 out of 20, which then we would be able to do, we could do half and half again. So or 10, yeah, and 3.5. So then we can do 3.5 out of 10, which is going to give us 0.35 or 3.5%. All right, or I'm sorry, 0.35, which is 35%. Okay, so that's one way to do it. All right, so now we're going to turn the page and we're going to start looking at our pass fail. So this one, we may need to go to our, if I can get this to work, I'm going to go to our online resource. So if you go into Canvas, okay, so I'm not going to give you a bag with paper slips in it. What I'm going to do is we're going to take 10 playing cards, 1 through 10. So all the number cards, we'll use aces as ones. And what we're going to do is even and odd. So even is going to be pass and odd is going to be fail. And so what you're going to do with your partner, and if you're at home, you can do this as well. What you're going to do is you're going to take those 10 cards and you cannot see them inside. So keep them upside down so you don't see the number. And you're going to draw 10 cards, 1 card at a time, 10 times. So you're going to draw 10 cards and see the order it is in. You're going to record the number of slips marked even for pass, and then that's what we're going to be looking for, the evens. So what I want you to do, I'm sorry, you're going to use 20 cards, not 10, 20 cards. So you're going to pull 10 out of the 20. That was my bad, sorry. Go ahead and do that, and then go ahead and mark your results on that page. We are still on page 234, so go ahead and do that. And then in class, we'll create a dot plot. Okay, so if I were doing this by myself, this would be what I got. So we got 5 out of 10 were marked even, passes, right? From the results of the first trial, we want to estimate the proportion of the slips in the bag or our cards that were marked pass. So 0.5, because since this was 5 out of 10, that would be 1/2. This is the proportion of slips marked even or pass for our group. So when I did this 5 other times, here were the numbers that I got. You're welcome to look at those numbers as well. Down. Okay, so now if we turn to the page, here is my dot plot that we got from class. So go ahead and hit pause and copy this down. And then for this is the proportions of our even cards that we pulled. And then from the class dot plot, we wanted to estimate the proportion of slips marked pass in the bag, and we want to explain our reasoning. And we're going to say 0.7, and it's pretty clear why it would be 0.7, but that's because the proportion that came up the most and the most and all other values seem to be centered around that. So if we look at that, we can see how tall this one is. And then we can see that everything kind of surrounds it, and the majority of our dots are around that 7. All right, so now we're going to move on to this fly memory. So go ahead and go to the bottom of page 235. And we're going to be doing this. So a biologist is breeding fruit flies to include a specific genetic mutation that will be useful in understanding memory in humans. To check whether the fly has a mutation, a DNA sequence is analyzed in a way that it kills the fly, so that the biologist only wants to test samples of flies to estimate the proportion of flies that have the mutation. So the biologist selects 40 flies in the sequence at random, because remember, we always want to be random, and finds that 9 of them have the genetic mutation. Based on this sample, estimate the proportion of flies in this group that has the genetic mutation. So go ahead and, well, I already have the answer here. So about 0.255. And that's because if we say 9 out of the 40 and we type that in our calculator, that is what we're going to get. Okay, so back to our fruit fly question. So we said 9 out of 40. And then this one, let's see if I can get it to go. There we go. The scientist is worried that only having one sample may not be reliable for estimating the proportions of flies with the mutation, but does not want to sacrifice more flies to get a larger sample. The proportion from the sample is a good estimate for The proportion from the sample is a good estimate for the population proportion, but it is difficult to understand the possibility of variability from a single value. Andre has a suggestion for how to better understand the variability. So we're going to look at 2A, and what I want you guys to do is read through that question and then try to answer the bottom of this question and see if it works. So Andre is suggesting you use 200 pieces of paper and mark 45 of them as mutant and then puts them all in a bag. And since Andre has decided to use 200 pieces of paper, why would 45 of them want to be marked mutant? What do you guys think? And so hopefully what you guys think is that 45 out of the 200 would be the same proportion as 9 out of 40. So 45 out of 200 is the same as 9 out of 40. You also could have used 40 pieces of paper and marked 9 mutant and 80 pieces of paper and marked 18 mutant. So there are different ways of doing this, but how he got the 45 was that is what's proportionate to what we found earlier. So then Andre, let's go to B. So then Andre simulates the scientist sample by drawing slips of paper from the bag, noticing whether it is mutant or not, then replacing the paper into the bag and drawing another paper until he has a sample of 40. He repeats this process for 50 trials and creates the dot plot right below that you can see in your book. So what I want you to do is estimate the values on the dot plot, a range of proportions that include about 95% of the proportions from the trials. So go ahead and hit pause and do that. So remember that you want to find 2 standard deviations away from the mean. So you're going to want to find the mean, right? And if we're just estimating, then what I would do is look at that and see what is about 95% and what feels like it's going to be about 95%. So I would say that would be like 0.1 to 0.3, right? We're looking at from here to here, and that's going to be about 95%. So Andre then finds the mean proportion. So now we're finding the average of the sample proportion, which is a little bit different than what we have done in the past. And so when we're finding the mean proportion from this, he finds it to be 0.2195, and then the standard deviation is going to be 0.06. So how far are your values from the last question from the mean? And then this is going to represent that margin of error. So remember, we have to do the margin of error. If we know that our standard deviation is 0.06, then we need to multiply that by 2, and we're going to get 0.12. And then we know that the mean is 0.2195, and we can subtract 0.1, and we end up with about 0.12. So then we're going to divide the distance. So this is C. Divide the distance from the last question. From the last question and by the standard deviation to get the margin of error in terms of the number of standard deviations. So we've done this. We did this in the last part of the unit. So go ahead and hit pause and do that. So hopefully you remember that when we do this, if we did 0.12 divided by 0.06, we should get 2, which is 2 standard deviations from the mean. We expected to see that because we know that the margin of error is going to be 2 standard deviations away from the mean. So based on Andre's simulations, should the scientists feel confident that the proportion of flies is within 2 standard deviations of the mean of the simulations? Yes, because we estimated that about 95% of the proportions from the simulations were within 2 standard deviations of the mean, which is exactly what we're looking for. So go ahead and we're going to do the cool down. Let me see if I can find that for us. So what does it mean to be 95% confident that the population proportion is within the margin of error of the estimated proportion? It means that there is 95% chance that the actual population proportion falls within that interval, which is what we're looking for. And what does it mean when we say that the population proportion is 0.45 with a margin of error of 0.2? That means that there is a 95% chance that the actual population proportion is going to be in between 2.5, I'm sorry, in between 0.25 and 0.65. And then have you ever seen the concept of margin of error in another class, the news, or somewhere else? So in class, we talked about this news article, and I'm going to pull it up right now. I'm going to show you how they talk about margin of error. Okay, so this is some polling data. Donald Trump leads in a new 2024 poll, but Joe Biden appears to be closing the gap. Okay, so this is from USA Today, and they posted this 2 days ago. So this isn't very old. And right here it says that the survey released Sunday shows Biden polling at 44% and Trump polling at 46%. And the chance from and that's a change from January when 42% of the voters said they would support Biden and 47% said they would support Trump. Okay, so that's a lot of numbers, but here's our sample. The poll of 1,000 registered voters conducted via cell phone was between April 12th and through the 16th, has a margin of error of 3.1%. So there you go. There's that margin of error that we've talked about. It's 2 standard deviations away from the mean, and it's going to take 95% of our data. But our 1,000 registered voters, this is via cell phone. So this could be that a lot of young people are answering because they don't answer phone numbers they don't know. Could be a lot of different things. Now let's see what that margin of error actually means. So because that margin of error is larger than Trump's apparent advantage, it may be tough to truly determine who has the lead. So basically, this isn't telling us a whole lot because our margin of error is too high. So that's somewhere in real life where we've seen this kind of wording and data, and we are using this. Okay, and then if you have any questions about margin error, please come to class with those questions. Otherwise, I will see you all tomorrow. Have a great day.